Welcome to The Explainer. Today, we're taking a deep dive into the sheer scientific ingenuity required to turn, well, basically dirty rocks into the technological world all around us. It's an absolutely fascinating journey. We're going to trace the steps from raw, untouched Earth straight to the smartphones in our pockets and the buildings we live in.
Think about this for a second. Airplanes, skyscrapers, miles and miles of electrical wires. These everyday marvels absolutely rely on metals. But how do we actually unlock these incredible materials from the solid Earth? They aren't exactly just lying on the ground waiting for us to pick them up.
Okay, let's dive into this. About 80% of all the elements out there are metals. And if we look at the Earth's crust, right behind oxygen and silicon sit two of our most crucial metals, aluminum at 7.6% and iron at 4.6%. So they're incredibly abundant, but they're completely hidden away, locked up tightly in complex chemical combinations.
Now, to actually pick those chemical locks in the Earth's fault, we need to establish a couple of ground rules early on. First up, we have ores. These aren't just any old rocks, they are metallic minerals from which metals can be profitably extracted. Because, let's face it, we aren't doing this just for fun, it has to make economic sense on a massive industrial scale. And the process of actually doing that? That's metallurgy, the step-by-step extraction of those metals from their ores, stripping away all that unwanted rock, which we call gangue.
So here's our roadmap for today's explainer. We're going to start with the reactivity cheat code, which is really our ultimate scientific rulebook here. Then we'll look at aluminum in the Hall process, iron in the blast furnace, and copper via electrolytic refining before we wrap things up by exploring the nonmetals.
All right, let's jump right into section 1, the reactivity cheat code.
And this brilliantly illustrates how a metal's unique chemical personality dictates the exact industrial process we need to extract it. You simply can't treat aluminum the same way you treat copper. It's kind of like a hierarchy of chemical stubbornness. At the top of the reactivity series, you have highly reactive metals. They're strong reducing agents, which basically means they hold on to their bonds fiercely. They are incredibly hard to extract. These stubborn, active metals demand extreme electrical methods to break them apart. But down at the bottom of the series, you've got less reactive metals. They're strong oxidizing agents and are much, much easier to extract. Honestly, sometimes they just need a little roasting and heat to let go of their rocky prisons.
So where does aluminum sit on our list? Right at the very top. Let's get into section 2, aluminum and the Hall process.
Because aluminum sits right near the top of that reactivity list, we can't just throw it in a fire with some carbon and hope for the best. No way. We have to literally beat this unbreakable metal into submission using massive electrical currents. Here's how that chemical ingenuity plays out step by step. We start with bauxite, which is the chief ore of aluminum. First, we react that bauxite with sodium hydroxide to strip away impurities like sand and iron oxides. Next, we use an acid treatment to precipitate out aluminum hydroxide, and then we heat that up to form pure aluminum oxide. But the main event? That's electrolysis. We run a massive electric current through the molten material using graphite electrodes. That electricity forcefully rips the chemical bonds apart, transforming raw bauxite into the incredibly light, strong metal we use to build airplane wings.
Now, here's a really surprising fact. The secret ingredient to this entire process is actually cryolites. You see, pure aluminum oxide melts at an absurdly high temperature. So we add cryolite to act as a solvent, and that dramatically drops the melting point. Without it, melting aluminum oxide would be an almost impossible, ridiculously energy-draining task. It is a brilliant chemical workaround that literally makes the whole aluminum industry possible.
Moving right along to section 3, iron and the blast furnace.
Now we're moving down our rulebook to an intermediate metal. Iron is the ultimate heavy lifter, absolutely essential for our construction and our massive skyscrapers. Because it sits a bit lower on the reactivity series, we don't need expensive electricity here, we need a colossal chemical reaction. Now, what's really interesting about this slide is the sheer scale of the blast furnace and how carbon monoxide acts as the chemical key. It's not just a big fire. First, we burn coke, which is a pure form of carbon, and that oxidizes to create carbon dioxide and a huge amount of heat. But wait, that CO2 is then reduced by more carbon to become carbon monoxide gas. And here is the magic. That carbon monoxide gas rises up through the furnace and actually strips the oxygen right off the iron ore, leaving behind pure, molten metallic iron just pooling at the bottom.
So what actually comes out of that fiery beast? Well, first we get pig iron, directly from the furnace. It's loaded with carbon, which makes it pretty brittle, but it's perfect for casting heavy things like domestic boilers or water pipes. Now, if we purify it up to about 99.5%, we get wrought iron.
That stuff is tough, it's malleable, and it's great for things like ornamental gates. But the real star of the show? That's steel. By carefully controlling the carbon and adding other elements through the basic oxygen process, we create the ultra-strong alloys that quite literally build the modern world.
Next up, Section 4, Copper and Electrolytic Refining.
Copper is our electrical wire champion, right? It's the metal powering your home and the device you're probably using right now. Sitting even lower on the reactivity series, it's a lot easier to extract from its ore, usually chalcopyrite. We can extract it with a simple chemical reduction, which gives us blister copper. Now, blister copper is about 98.5% pure. That's good, but honestly not good enough for high-end electronics. So the crucial point is, to conduct electricity without resisting and burning up, we need a highly specific final process to achieve absolute flawless purity. In refining, we make a massive block of that impure blister copper act as our anode. We place it in a bath of aqueous copper sulfate. When we turn on the juice, pure copper ions leave the impure block, travel through the liquid electrolyte, and deposit themselves onto a super thin cathode. The final result? Pure copper, ready to wire the globe.
And finally, Section 5, Exploring the Non-metals. Let's flip the script a bit. Let's move to this table and see how this builds on what we've learned. We're looking at the other side of the periodic table now. Non-metals only make up about 20% of the elements, but they are just as vital. We're talking nitrogen, oxygen, sulfur, and chlorine. They essentially present a picture of complete opposites to everything we've just covered. Where metals are lustrous, malleable, and electropositive, non-metals are dull, they're brittle, and they are electronegative, meaning they are total electron thieves. And of course, while metals are the ultimate conductors of heat and electricity, non-metals are decidedly poor at it.
To give you a quick non-metal case study, let's look at how we extract chlorine. It doesn't really occur freely in nature. It mostly hides out as sodium chloride, which is just regular salt. Commercially, we extract it through the electrolysis of brine, which is basically just super salty water. We run electricity through that brine, and poisonous, greenish-yellow chlorine gas bubbles up at the anode, while water is reduced at the cathode. Now, that gas might be highly toxic, but paradoxically, it's an incredibly useful bleaching agent and the exact disinfectant we use to kill bacteria and make our drinking water safe.
We have covered a ton of ground today, from zapping bauxite with electricity to make airplanes, to roasting iron with carbon for our skyscrapers, to splitting salt water just to keep us safe. So, I want to leave you with this thought. Next time you walk down the street, take a second to look around. Can you see the massive scientific ingenuity hiding in plain rocks? The entire modern world is a testament to our mastery of these chemical rules. Thanks for joining me on this explainer, and keep questioning the amazing science hidden in the world around you.